So hi and hello there, welcome to the new video of the course, and in this particular video you would be understanding the concept of DJ lights, or basically dancing LEDs. So I hope you might have seen that in DJ lights the light switches on and off continuously according to the beats of the song, right? So this is what we are going to see in this particular video. Okay, so at the end of this particular video, or at the end of this particular session, you would be in the situation to understand and design, and also you would be able to implement the concept of DJ light with the help of a single transistor, as you can see over here on this particular screen. Right, so now what we'll do, we'll see the block diagram of this particular mini project. And as you can see, since we are dealing with the DJ lights, or basically dancing LEDs, so we would be requiring one audio signal, right? So let's suppose this is your audio signal. Then what we would be doing, we would be fetching this particular audio signal to our controlling block. And since in this particular course we are dealing with BJT, so obviously the controlling block is nothing but the BJT. And we have to bias this BJT in such a way that it should be almost equivalent to 0.7 volts. That means what? The input side, or the input voltage, that means what? Voltage between the base and emitter, it should be exactly equals to 0.7 volts. Okay, so the reason I will tell you later on. Okay, but as of now, just understand that why we need to we need to bias this particular transistor at 0.7 volts only. Okay, we need not to go above 0.7 volts or below 0.7 volts. Okay, we need to bias it exactly at 0.7 volts. Okay, then obviously we need to see the output with the help of LED. Okay, so this is how the block diagram will look like. Okay, so let me proceed further. All right, so now here we need to be very much cautious about the selection of the LED. So as you can see, there are purple 1 2 3 4 5 6 and 7 types of LEDs. This is purple, red, orange, yellow, green, blue and white. Okay, we need not to worry about the what I can say, the structure part, or basically the its material part, like it is made up of gallium and arsenide and all. We need not to worry about this particular part. What we need to worry about is this. See, since we are dealing with the um, electronics part, so we need to worry about this particular section, that is voltage and the current section. So as you can see, for purple color LED to glow, it requires at least 1.2 volts and 20 milliamperes. Okay, so according to this particular chart, what exactly this particular row, okay, it is trying to tell, or what exactly this particular column, sorry, not row, what this particular column is trying to tell is this. See, for purple LED to glow, for purple LED, purple color, for purple color LED to be in on condition, or to glow, to be in on condition, to be in on condition, or to glow, it requires at least 1.2 volts. Okay, 1.2 volts and 20 milliamperes of current, 20 milliamperes of current. So this is the minimum threshold voltage and minimum threshold current required for the respective LEDs. Okay, so as you can see, for the red LED to glow, the minimum voltage required is 1.8 volts. Okay, so VRED, that means what? The red color, sorry, the red LED to glow, the minimum voltage required for the red LED to glow, it is 1.8 volts to 2 volts, roughly 1.8 to 2 volts. Okay, this is the minimum threshold voltage, and obviously the current required for the red LED to glow is 20 milliamp. So the current is same for all the cases. The current is same in all the cases, or the current required, or the minimum threshold current required for all the LEDs to glow is 20 milliampere. Just the thing is that the voltage is changing. Okay, and obviously the wavelength is also changing. Okay, so we need not to worry about this particular part. See over here. Okay, we need not worry about this particular part. What we need to worry is this. That means what? For purple color LED to glow, we need 1.2 volts and 20 milliamperes of current, right? For green, 3.5 and 20 milliamperes. For white, 4 volts and 20 milliamperes of current, right? So this is what we need to worry about it. Okay, so what I will do, I'll erase this particular section. Okay, I will erase each and everything that I had written over here, and so that whenever you refer my notes, you should understand what exactly it is. So what I will write over here is this only, right? So wait, I will take certain different color which is not present in this particular chart. Just a second. Yeah, maybe this one. So this is the minimum threshold current, minimum threshold current, threshold current to switch on the LED, to switch on the LEDs, right? To switch on the LEDs, right? LEDs. And these are the minimum threshold voltage. Just a second. These are the minimum threshold voltage to switch on the respective LEDs, right? Minimum threshold, minimum threshold voltage to switch on the respective LEDs, to switch on the respective LEDs, right? And one more thing I would like to add over here is that, see, this is the minimum threshold voltage required to switch on the red LED, right? And this is the minimum threshold current required to switch on the red LED, right? But all the LEDs can bear up to 5 volts. That means what? That means if I'm giving 5 volts to this particular red LED, it will glow. But if I'm giving more than 5 volts, there is high probability or high amount of chance that this particular LED will burn out, right? So the maximum threshold voltage required for the LED, it is 5 volts. Okay, so what I will write over here, the maximum, this is a short note from my side or based on my experience. Okay, as such you won't get any theoretical proof anywhere, but in my labs what I had done, I had intentionally given 5 volts, 6 volts, 7 volts to certain LEDs, and what I had seen over there was uh, all the LEDs or maximum amount of LEDs can bear voltage up to 5 volts, but if I'm exceeding that voltage above 5 volts, the LEDs may burn out completely. Okay, so this is kind of a note from my side, or a short kind of pointer from my side to you all guys. uh, the LEDs can bear maximum 5 volts of current. Okay, so maximum sorry, not 5 volts of current, 5 volts of voltage. So maximum 5 volts, maximum 5 volts of voltage, maximum 5 volts of voltage can be sustained by any LED, or can be bared by any LED. That means what? LEDs may burn out if I'm providing more than 5 volts of voltage, right? So just a second. So maximum 5 volts, maximum 5 volts of voltage can be sustained or bear by any LED. Okay, I know I'm not grammatically that strong, but try to understand this, because whenever you are learning some technical subjects, so you need not to worry about the grammatical aspect of it. Okay, so that means what? If I'm supplying more than 5 volts to any LED, if I'm providing any voltage which is greater than 5 volts, if I'm providing any voltage to any LED which is greater than 5 volts, which is greater than 5 volts, so there is high amount of chance, high amount of chance is high amount of chance that the LED may burn out completely. Oh, sorry. LED may burn out completely. Okay. So this is one of the most important point you should note. Okay. But in case of white LED, the chances is very less. Why? Because the minimum threshold voltage to operate this white LED, it is 5 volts. Okay. All right. So moving forward. Okay. So what I'm doing, I am considering any three LEDs for you to explain this particular scenario. What I had considered over here is this. That means what? I had considered these three LEDs. That means red one, this one, then yellow, and then yellow, and then green. So I had taken these three LEDs into account. Okay, and with the help of this particular LEDs, we are going to make a kind of DJ system or DJ light LED or dancing LEDs. Okay, so I had taken this one, and this one, these three LEDs, that is red, yellow, and green. Okay, just because this is a kind of traffic light as well, red, yellow, and green. So that's the only reason that I had taken these LEDs. Otherwise you can take any 3 to 4 combination of LEDs. It's up to you. You can take purple, red, orange, and yellow. You can also go with white, blue, and green. Okay, but since you are taking these LEDs, okay, you need to alter, or you need to change the voltages and all, which we would be saying voltages and current. Okay, based on the color of the LEDs that you are selecting, you need to change the design of the circuit as well. Okay, all right. So what I can see over here is that for red LED we require 1.8 volts, for yellow we require 2 volts, roughly 2 to 2.2 volts, and for green we require 3.5 volts, okay, to operate green LED. And the current for all of this LED, it is 20 milliampere, right? So the current will remain same in all of this scenario, but the voltages, they are changing with respect to each and every LEDs. Okay, so what I can see over here is this. That means what? The maximum voltage that I can supply to the system, okay, or what I can say, the maximum voltage that I can supply to this particular LED, it is 3.5 volts. Okay, so what I can say is that my VCC, this should be 3.5 volts, or basically I would take V only. Okay, so that you should not get confused over here. So what I can say over here is that my voltage should be 3.5 volts. Okay, apart from that, since I am dealing with 3 different LEDs, this is red, right, then yellow, and then green, right? So each LED requires 20 milliampere of current. As you can see over here, each LED requires 20 milliampere of current to operate. So 3 into 20, that means what? 60 milliampere. So I may require, or basically I require at least 60 milliampere of current to switch on this LED. So I is equals to 60 milliampere. Okay, sorry. So these are the two important parameters that we had seen, or that we had got from this particular table. Okay, so what we had obtained from this particular table is this. That means what? We require at least 3.5 volts, okay, to switch on this LED. Okay, and as you can see, 2 volts is less than 3.5 volts, so obviously it can easily operate yellow color LED. And again 1.8 volt, it is less than 3.5 volts, so it will also operate, or it will also switch on the red color LED as well. Okay, and since for green color LED to be in the on condition, it requires 3.5 volts. So that means what? With just by selecting one voltage, we would be able to switch on all the 3 LEDs. Okay, so this is what we had seen as of now. So that's why we had taken only this voltage. Okay, we cannot take this one, this one or this one, because let's suppose if I'm taking this particular voltage into account, so in that particular scenario, this green LED would not be able to be in the switch on condition, right? So it's absolutely fine, or it is advisable to select this one, that means 3.5 volts, since we are selecting red, yellow, and green. So for that combination we are selecting 3.5 volts and 20 milliampere of current. It is same in all of these three scenarios. So 20 into 3, why? Because we are dealing with 3 LEDs, right? So 20 into 3, that is 60 milliamperes. So these are the two parameters that we had taken into account, right? All right. Sorry. So as you can see over here, sorry, this is VCC, that is 3.5 volts, and that's why we had taken V over here 3.5 volts. Okay, and this is the current or the output current, that is IC 60 milliamperes. Now you would say, sir, why we had connected over here in this way? So if you could remember, in the previous two sessions or in the previous two projects, we had connected LEDs to the collector side. That means what? The collector contains the load resistor. Now you would ask me, what is load resistor? So this load resistor is nothing but the LEDs. That means what? The output, okay, the output components or the output resistor, we are connecting it to the collector side. Okay. All right. So now, being a student, you would ask me, sir, should we go with this particular setup or should we go with this particular setup? Okay, in both of the cases we are getting, see over here we are getting 60 milliampere of current which will flow in this particular direction, right? Over here as well, this particular IC will flow in this particular direction. Okay, that is 60 milliampere, and in both of this particular scenario we had connected 3.5 volts over here. Okay, that means this is our VCC. So let me write over here, this is our VCC. Over here as well, this is our VCC. Okay, so now just try to think in this way, my dear student. As you can see, let's suppose if I'm connecting it in this way, that means in series. So let's suppose if I'm connecting this particular LEDs in series. Okay, so now what is going to happen? Forget about what are the input voltage we are getting. Okay, or let's suppose the input voltage we are getting, it is greater than 0.7 volts. So if it is greater than 0.7 volts, so then what is going to happen? Obviously IB is greater than IB is maximum in this particular scenario, and if IB is maximum, so IC will also increase, and as IC will increase, so obviously this particular voltage, that means voltage drop across VC, it is going to decrease, and due to this the current will flow in this particular direction. But then what is going to happen is this, see, in series combination what is going to happen, this green LED will glow first, then yellow, and then red, right? But in case of parallel, what is going to happen? This IC will get divided in this way. Okay, so this would be, let's suppose this is IC1, this is IC2, this is IC3, right? So this IC would be getting divided into 3 ways, or basically 3 parts. Okay, and then what is going to happen? See over here, green LED will glow, and at the same time red will also glow, and at the same time yellow will also glow. Why? Because IC is moving in the, although the IC is not same. Okay, over here the IC was same, and over here the IC would not be same. Okay, but it is moving at the same time and in the same direction as well, right? So let's suppose at t is equals to 0, IC is present somewhere over here, but at t is equals to 1, that means at time t is equals to 1 second, IC1 will flow in this direction, in this way over here, and at the same time IC2 will flow in this particular direction, and at the same time IC3 will flow in this particular direction. That means what? At same time IC is flowing in all of these 3 LEDs, but over here, let's suppose at t is equals to 0, this is where your IC was, this is where your IC was at t is equals to 0. At t is equals to 1, this green LED will glow. Why? Because your IC was over here in this particular direction, so this was your IC. Okay, at t is equals to 2, your IC was over here. Okay, it is flowing in this particular direction, and at t is equals to 3 seconds, I will write seconds, obviously it won't be in minutes as well, so your IC would be in this particular direction. But what we can see over here is that when we are talking about t is equals to 3 seconds, this green LED is in the off condition. Why? Because the current has already been moved in this particular direction and it is present over here. Okay, at instantaneous movement the current is present over here. Okay, but in this particular scenario, since the IC is getting divided equally, or even if it is not getting divided equally, but at the constant time or at the instantaneous time, all of these three LEDs will glow. Okay, so it's preferable or it's advisable to select this particular circuit. Why? Because we'll see after some time that why we are selecting this one and not this. Okay, why? Because these LEDs will switch on and off one after another, like green will glow, then red, then yellow, then red. Over here all of these three LEDs will glow at the same time. And the reason we will see when we will simulate this circuit. Okay, so let me erase this particular thing. Sorry, let me erase this particular thing. So this one, or let it be as it is, because whenever you will refer my PDF, you would be understanding that why we had considered this one and not this one. Just a second. Let me erase this thing, and what I will do is this. See, we are not selecting this one, and we had selected this one. Okay, we had selected this setup. Okay, so let me move further. Alright, so what we have is this. See, we have VCC, we have IC. Alright, so the IC is nothing but IC is equals to 60 milliamperes, right? IC is equals to 60 milliampere. So we all know that since we are dealing with BJT, and I told you in the very first session or in the introduction session that for BJT transistor we would be using BC547. Okay, so generally we would be using this particular transistor, that is BC547. So let me write over here, we would be using BC547. This is the BJT transistor. Oh sorry, BC547. This is the BJT transistor that we would be using generally in most of the scenarios, right, or in most of the application. Okay, and we all know that for BC547, the current gain or beta is 110, right? 100 to 110. But since we are designing the mini project, so it's preferable to take this particular value, that is 110. Okay, and we also know that what we know is this. See over here, that is IC is equivalent to beta times of IB. Okay, and now from here you can easily calculate the value of base current. Why? Because we have IC, we also know what is beta, so we can easily calculate the value of IB. So our IB is equivalent to IC by beta, right? IC by beta. Just a second, IC by beta. So your IC is nothing but 60 milliampere divided by beta is 110. So let me just calculate this particular value, and then let me check what exactly the value we are getting. Okay, so my IC is 60 into 10 raised to minus 3, right, divided by 110, and thus the value pans out to be 0.54 milliampere. Okay, so my IB pans out to be 0.545 milliampere. So this is the value for my IB or the base current. So let me just highlight this particular value by writing it over here. So my IB is equivalent to 0.545 milliampere. Okay, so this is the value for the base current. So let me just highlight it. This is the value for the base current. Alright, so what I had done over here, let me move to the next slide. So as you can see over here, this is how the circuit will look like. Now that we had got the value of IB, and as I told you in the block diagram itself that we need to bias this particular BJT exactly at 0.7 volts. The reason I will tell you later on. Just let me just complete this particular circuit. Okay, so that means what? We know the value of IC, we also know the value of VCC. Okay, and based on these two particular values we had calculated the value of IB. Alright, and then what we also know, or what we should do over here is this. We should intentionally bias this particular BJT voltage, VBE or the base emitter voltage exactly at 0.7 volts. So VBE should be exactly at 0.7 volts. But to bias exactly at 0.7 volts. Okay, and then what we can do, we can apply KVL to find out this particular base resistor. Okay, we should apply KVL to find base resistor, because as of now we know everything apart from this base resistor. Once if you know this value of base resistor, then our circuit is 90% completed. Okay, so what we are going to do over here is this. Let me just move this particular thing over here slightly to the right side, just a second, and then let me apply KVL in this particular direction. So I'm applying KVL in this particular direction, and this is then it is going to ground, right? So yeah, I'm applying KVL in this particular direction. So I'll write over here applying KVL to the base emitter loop. Let me take certain different color. Yeah, applying KVL to the base emitter loop. That means this one, this is your base, right, and this is your emitter. Okay, so as you can see over here, we are going from this particular terminal, right? So it is plus 3.5 volts, or just a second, I will draw it over here. So it would be something like this. Just a second, just give me a few minutes. I'll draw it roughly so that you should be able to understand it. So let's suppose this is your plus 3.5 volts. Okay, try to understand it as we are solving in the numericals. Okay, we are actually opening this particular circuit. Why? Because we need to take the base emitter loop. We are not at all interested in the collector emitter loop, right? So basically we are opening this particular circuit, and then what we can see over here is this. So this is your base terminal, then this is your resistor RB, right, and then this is your transistor, that is the base of the transistor. This is your emitter, and then it is getting grounded, right? Yes, then it is getting grounded. We are not at all interested in the collector aside. Why? Because we just need to understand, or sorry, we just need to find out the value of RB. So this is your RB. What we know is this, that is the value of IB. So the value of IB is 0.54 milliampere. Okay, so this is the value of IB. So this is the value of IB which we had already got over here. Okay, we are not at all interested in the value of IE. Okay, as it is already grounded, right? So by applying KVL to the base emitter loop, and obviously this is your VBE, which is 0.7 volts. So this is your VBE, which should be strictly equals to 0.7 volts, right? So as I'm applying KVL over here, so this would be plus 3.5 volts minus of IBRB, right, minus of IBRB minus of VB. As I told you, whenever you are moving in the opposite direction, so this is your plus minus, right, this is your plus minus. So when you are moving from top to bottom, you should always take into account the opposite sign. Okay, and the opposite sign is minus in both of these scenarios, so that's why I'm writing minus IBRB and minus VBE, right, VBE, and then it is equivalent to 0. Okay, I hope you know how to apply KVL, as we had already learned this particular topic, so I'm not explaining you it in depth. Okay, so this would be plus 3.5 volts minus VBE is nothing but 0.7 volts, and then what we are doing, we are moving this whole of the term to the RHS side. That means what, this particular term to the RHS side over here. So this would be equivalent to IBRB. Okay, so this is equivalent to IBRB. Sorry, IBRB. Alright, so now that we are knowing the value of IB, so we can easily calculate the value of RB, right? So my RB would be equivalent to 3.5 volts minus of 0.7 volts divided by what is the value of IB. The value of IB was 0.545 milliampere. Okay, so 0.545 milliampere. So this is the value of IB. Just a second, so let me just calculate this particular value. So this is 3.5 minus of 0.7 divided by 0.545 into 10 raised to minus of 3, and thus this value pans out to be 5.137 kilo ohms, right? So the value of RB pans out to be just a second, I will take this one here. So the value of RB pans out to be 5.137 kilo ohms. 137 kilo ohms. So this is the value of the RB. Okay. You can also consider as 5 kilo ohms. Okay. Let me proceed further. Alright. So now what we have got is this. So the value of RB is 5.137 kilo ohms. Okay, so we know the value of RB. Now what? See, we had completed the circuit. Okay, we had completed the 90% of the circuit. Okay, so now what we'll do, first we'll simulate this circuit, okay, with the help of audio signal, and then we'll check the output for it. Okay, just a second. But before simulating this, I would like to explain it again. Okay, so this was your block diagram. What we had done, we had connected this audio signal, or basically we had not connected as of now. We are going to connect this particular audio signal. Okay, so we are going to connect this audio signal with the BJT transistor, and this was your LED. Okay, so let me move over here. Alright, so here we are going to connect the audio signal over here. This is your controlling block. So this is your controlling block. Okay, controlling block, and these three LEDs, they are nothing but your output, right? These three LEDs, they are nothing but your output. So let me erase this particular thing, because whenever you will refer PDF, it won't look that proper, right? And that's why I had explained this particular part in the video itself. Alright, and then as you can see, we had biased this particular transistor strictly at 0.7 volts. Okay, so basically we had seen these three aspects, or these three components of the block diagram. Okay, we are only remaining with this one. Okay, so this we are going to simulate it in the Proteus software. Okay, so let me move to the Proteus software. Just a second. Alright, so first of all, we'll only simulate this particular circuit. Just a second, let me move to the Proteus software, and let me erase all of these things. Just a second, let me erase all of these things, or delete all of these things. Alright, so as you can see over here, this is the same circuit which we had designed. Over here I had taken 5 kilo ohms of resistor. Over here we had got 5.137 kilo ohms, right? So it's absolutely fine even if you take 5.1 or 5 kilo ohms, it hardly matters. Okay, and these are the three LEDs, that is green, red and yellow, and as you can see over here, we have taken green, yellow and red. It's absolutely fine even if you interchange it, the result would be same in both of the scenario, right? Sorry. And over here, as you can see, we had taken 3.5 volts. This is your VCC, right? And rest of the circuit is same. This is your BC547 transistor. Okay, and then what we'll do, obviously we need to provide over here the input signal, and the input signal is nothing but the audio signal, right? So we need to connect one audio signal over here to the base of the transistor, right? So what I'm trying to tell over here is this. Over here, what we need to do, we need to provide one audio signal. We'll take this one only. Okay, so over here we need to connect one audio signal. So this is grounded, right? So this particular part, it is grounded, and in between both of them we need to provide audio signal, something like this. Just a second, sorry. Yeah, we need to provide one audio signal. So this is your audio signal. Okay, so that means what? That means this particular, I'm talking about this particular component. Okay, I'm talking about this particular component. Alright, so in the Proteus software, how you should provide this particular audio signal. Okay, so for that, just a second. So for that, what you need to do, you need to go over here. As you can see, this is kind of signal generator mode. You need to go in the generator mode, and then you have to select over here audio. Okay, and then you have to connect this particular pin to the base of the transistor. Okay, over here, and this is the oscilloscope, as you can see over here. This is the oscilloscope, and I had connected the yellow wire to the base of the transistor. Okay, and then to give the audio signal, obviously you need to have one audio signal, so you have to click over here, and over here the audio signal should be in the wave format. Okay, WAV. It should not be in the MP3 or MP4 format. It should be strictly in the wave format. So since I was having one audio signal which is in the wave format, so as you can see, chilling music dot wave, it can be any audio. Okay, it can be on any audio, you do not worry about it, but it should be strictly in the wave format or the wave audio file. It should not be in the MP3 or MP4. I'm repeating it again. The audio signal or the audio file should be in the wave format. It should not be in the MP3 or any other format. Okay, so I had selected it over here. Okay, and now we'll run this particular circuit. Alright, so as you can see, I'm giving the audio signal. Just a second, let me move it down. Alright, oh sorry. Alright, so this is the audio signal, and in the oscilloscope I can see that I'm fetching the audio signal, but the LEDs are not glowing. Okay, so there might be some problem, and this can be a severe issue. That what exactly the problem is. Why? Because we had completed this circuit successfully, right? But the project, or basically the circuit, is not working. So what can be the problem? If you could remember, in the previous course of the analog electronics, I told you that just a second. Alright, so in the previous session, if you could remember, I told you that there is one component which is used to block the DC signal and which is used to pass the AC signal. If you could remember it clearly, or if you could remember, I don't know whether if you had enrolled in the very first, sorry, in my third course, or basically in the very first course of the analog electronics or not. But at that particular time, I told you that there is one component which is responsible to block the DC signal and pass the AC signal, and that name of the component is capacitor. So basically, what is the function of the capacitor over here? Oh sorry. So this particular capacitor, it has two functions, or two primary functions, that is to block the DC signal. So the first function is to block the DC signal, direct current. Okay, to block the DC signal, right? And the very second function of the capacitor is to pass the AC signal, sorry. That means what? That means it provides high resistance to DC signal, right? High resistance to DC signal, and provides negligible or low resistance, or acts like a short circuit to the AC signal, low resistance path to the AC signal. Okay, and since, if you could see very clearly in this particular simulation, just a second. Yeah, as you can see over here, this particular yellow signal, or this particular signal, it is your AC signal. I will write over here only, this is your AC signal. Why? Because it is fluctuating down and up, down and up, down and up, right? So as I told you earlier, this fluctuating signal is nothing but your AC signal. So let me erase this particular thing, and that's the main reason. Since we had not connected our capacitor over here, so that's why these LEDs are not glowing. Why? Because this AC signal, it is not able to superimpose to the base, superimpose with the base voltage. So that's the reason. The LEDs are not fluctuating, right? So let me pause this particular thing, just a second. Yeah, let me pause this particular working of the circuit, and let me move over here. All right, so as you can see, since there wasn't any capacitor over here, so basically what is going to happen, or what is happening over here, is that this audio signal, it is not able to sync with the base voltage, and that's why the LEDs are not glowing. Okay, so basically we have to connect, or we need to connect the capacitor, or the capacitor having the capacitance of 4.5 4.54 microfarad. Now you will ask me, sir, how you calculated this value? So we will see its calculation part in the amplifier section. Okay, we'll see the calculation of this particular uh, capacitance value in the amplifier section. So just a second, I will write it properly. Let me erase this particular thing, and let me just move this particular part over here, and let me write it all of these things properly, because it is not looking that well, right? To connect over here. Okay, so what I will do, just a second, let me erase this particular part. So I will erase this particular thing, and then I will connect one capacitor over here in this way. Okay, and the value of the capacitor would be 4.54 microfarad. 4.54, oh sorry, let me write it properly. 4.54 microfarad, right? So the value of capacitor that I need to connect in this particular circuit, it is 4.54 microfarad of capacitance we need to connect in the circuit. So this value of the capacitance we need to connect in the circuit. So we need to connect this capacitor in between audio signal and base terminal of transistor. Okay, so what exactly it will do, see over here, just a second. Yeah, so what exactly it will do, so as you can see, this is your DC voltage which is coming over here. So let's suppose there is some voltage drop across the resistor RB. Okay, let's suppose it, for time being, it is 2 volts. Okay, so this RB, the voltage drop across RB, it is plus minus of 2 volts. Okay, that means what, 3.5 minus 2, that is 1.5 volts. So 1.5 volt, it is getting reflected over here. So over here we are getting 1.5 volts, right? And this 1.5 volts, let's suppose if capacitor is not present, so it will go over here, it is 1.5 volts. And this audio signal, obviously the audio signal, remember one thing, it is in few millivolts, it is in millivolts. 1 millivolt, 0.1 millivolts, 2 millivolts, right? We don't know what exactly the voltage of this particular audio signal would be. Okay, and as you can see, 1.5 volt, it is greater than 0.1 millivolts or 1 millivolts. Okay, so what exactly it will do, it will push this particular voltage in this particular direction, right? So that means what, it is not able to superimpose on this particular higher voltage. So basically, in absence of capacitor, it was not able to superimpose, right? Just a second, let me erase it properly, then I will write over there only. So in absence of capacitor, see, I'm explaining you each and everything in depth, and I'm taking hell amount of time. I know I'm taking hell amount of time to explain each and everything, because I want that you should understand this particular concept in depth. Okay, so in absence of capacitor, it was not able, I mean the audio signal, the audio signal was not able to superimpose with the DC signal, or DC voltage. Okay, and therefore to superimpose weak audio signal on strong DC signal, DC signal, we had connected one capacitor, connected the one capacitor, okay, and the capacitor, okay, and the value of the capacitor, or the capacitance of the capacitor, it is 4.5 microfarad. And this particular thing, that how exactly we are able to calculate this value, we'll see it in the amplifier section, okay. How we calculated this value, how we calculated this value, okay. So this would be one question which would be arising in your mind, and we will see this in the amplifier section. We'll see this in the we will see it in the amplifier section. Just a second, we will see it in the amplifier section. We will see it in amplifier section. Amplifier section, okay. That means what, how we are using transistor as an amplifier. So at that particular time we will see it, that how we will be able to find out, or how we will be able to calculate the value of the capacitance of any capacitor, okay, which we are going to connect to the transistor, okay. So I hope up till here each and everything is crystal clear to you all guys, okay. And as you can see, now our circuit is completed by connecting this 4.54 microfarad of capacitor, and this is your audio signal. So this is your audio signal. So let me write over here, this is my audio signal, which should be strictly in the wave format, okay. It should be in the .wav format, .wav file format. I will write file format, okay, so that whenever you will refer PDF, you would be able to understand this. And the main reason that why I had connected this capacitor over here, so the reason is basically to superimpose, right, to superimpose weak AC signal on the DC signal. For superimposing, I will write in shortcut, for superimposing purpose we had connected this capacitor, okay. So now what we'll do, just a second, I think I had included, yeah, what we'll do, we'll connect one capacitor over here, and then we will see it's working, right. So let me move it over here, just a second, let me move this particular thing over here, and then what I will do, I will delete this wire as well, and then I will connect one capacitor. So as I can see, I will take polarized capacitor, okay, connect this part over here and this one over here, and then I will change its value. It should be 4.54, right, 4.54 microfarad. So it is 4.54 microfarad, okay. And then what I will do, I will put this over here, just a second, over here, yeah. And obviously this should be in the wave format, as you can see over here, .wav over here. I selected it over here, and then okay. And then what I will do, I'll run this particular circuit, and then I will check. Alright, so as you can see over here, this particular LED, it is glowing on and off with respect to the audio signal. I don't know whether you are able to see it properly or not, because my software, it is crashing a bit, okay, or it is hanging a bit. But yeah, over here now, as you can see, I had done nothing. Just by connecting this particular capacitor, we are able to see that with the help of this particular audio signal, okay, the LEDs are switching on and off, okay. That means it is switching on and off with respect to the bits of this particular song, okay, bits or whatever you call. I'm not so great in the music and all, so bits or pops or whatever it may be, okay. So with the help of this particular or basically, as you can see, as the amplitude of this particular audio signal, it is increasing, so your IB will also increase, right. As your IB is increasing, so your IC will also increase, and as IC is increasing, so voltage drop across this LED, it will increase, and on contrary, see the decreasing section of the audio signal. So as the amplitude is decreasing, so your IB will decrease, right? And as IB decreases, so your uh, voltage drop across this particular LEDs will decrease. Why? Because your IC decreases, right? And thus LED will remain off. So basically the back end or the concept behind this particular circuit is nothing but LED as a BJT as a switch. But just by connecting audio signal and just by designing this particular circuit, we had easily implemented this particular thing. And most importantly, that why we should keep this particular thing or keep this particular voltage, that means base emitter voltage, as 0.7 volts. Why? Because if the let's suppose if I'm giving 1 millivolt swing, just a second, I'll explain this particular concept over here, just a second. Alright, so now I will explain that why I had kept this 0.7 volts. Okay, why not 0.72 or 0.73? For this, instead of audio signal, we will assume sine wave signal. Okay, so as you can see, it is of one, the signal is of 1 millivolt. Okay, so for this particular part, that means for positive half cycle, let me write over here for positive half cycle. Let me decrease the thickness of the pen. Alright, for positive half cycle, this is 0.7 volts. Okay, and let's suppose this is 0.5 millivolts. Okay, so I'll add it, that means 0.7 volts, 0.7 plus 0.5 into 10 raised to minus 3 into 10 raised to minus 3, right? So the value pans out to be 0.7005, right, volts. So as you can see, this extra volts, that means 0.05 volts, this particular volts, it will increase the base current, right? See, try to understand this way. This is your 0.7 volts, and as you can see, for positive half cycle, this base voltage will increase. So over here you will get 0.7005 volts, and as this particular VBE, that means base emitter voltage, increases, so your IB will also increase, right? So your IB increases. Why? Because with the help of the input characteristic of BJT, we had seen over there, means IB versus, VBE versus IB, VBE versus IB. So with this particular characteristics, what we saw is this: as your VB is increasing, so your IB will also increase, right? And as our IB is increasing, so our IC will also increase. Why? Because IC is beta times of IB, right? So as our IB is increasing, so our IC will also increase, and thus, since we know that there is a not proportional relationship between IC and VC, so your VC decreases, right? And thus, as VC decreases, so voltage drop across the LED will increase, and thus LED will switch on. So this will be in on condition. Okay, and now let's suppose we are talking about the negative half cycle. So obviously now I need to calculate over here. So 0.7 volts minus 0.5 into 10 raised to minus 3, minus 0.5 into 10 raised to minus 3. So the value pans out to be, so over here during negative half cycle, you would get the value as 0.6995. Okay, as you can see, that means what the minimum threshold voltage required for a transistor to be in the on condition, it is 0.7 volts, right? But now over here we are providing 0.6995 volts. That means what? Your BJT would be in the off condition. That means what? Your IB will decrease. Okay, it won't be zero, but it would be decreasing, right? And as your IB will decrease, so your IC will also decrease, right? And based on this, what is going to happen? Since there isn't any proportional relationship between IC and VCE, okay, so what is going to happen? As your IC decreases, so your VCE increases. So over here VCE increases, and thus the voltage drop across this particular LED, it is going to decrease, and thus this particular LEDs would be in the off condition. So now think this particular sine wave as your audio signal. So for positive half cycle, this LED will glow. For negative half cycle, this LED will be in the off condition. And the same thing is happening over here. Just a second. Let me just run it again. Yeah, as you can see, during positive half cycle, the LED is in the off condition. During negative, it is in the off condition. Okay, but since this particular wave, it is moving very quickly, like positive, negative, positive, negative. So you are not able to see it clearly that for positive half cycle it is on, and for negative half cycle it is in the off condition, because it is the audio signal, right? And thus what is, with the help of this audio signal, we are able to design the circuit in such a way that the uh, LEDs are glowing on and off continuously, and thus we can say that we have successfully implemented the concept of DG light with the help of a single transistor, right? You might have seen that most of the guys have implemented the circuit using microcontroller or Arduino or processor, but with the help of single transistor, okay, we had implemented this particular circuit successfully. Okay, we had simulated the circuit successfully, but I had also implemented the circuit. uh, okay, and that I will put at the end of this particular video. But what I had done over there is that I had taken green, red and white LED, because I was not having this yellow LED, so I had taken white LED. But the concept of designing the circuit remained the same, right? So the voltage got changed over there. Why? Because the minimum threshold voltage required to switch on the white LED was 4 volts. Okay, so I had taken over there the 4 volts. Okay, so I hope that you understood each and everything in depth. I'm stopping the simulation and we'll again move back to the blackboard. All right, so I hope that you understood each and every concept in depth. I'm again explaining it very quickly. All right, so this was the concept of DG lights. Okay, so what I had done, I had drawn a block diagram over here, and as you can see, this is your audio signal, this is your controlling block and output LED. And now you are in the situation to understand this particular thing, right? So this audio signal is getting fetched to the BJT, then BJT is nothing but it is acting as a switch, right? It is switching on for this particular thing. See, for this particular time interval, that means up till here, BJT will act as a closed switch. That means what? It will switch on this particular LED, and during negative half cycle, that means this one, it will switch off this particular LED. And that's why we had intentionally biased this particular BJT at 0.7 volts. Okay, I hope you are getting my point. And then what is going to happen? See over here, I had intentionally taken this particular table. So the minimum threshold current to switch on the LEDs, it is 20 milliampere, and the minimum threshold voltage, it changes with the respect to LEDs, right? But maximum 5 volts of voltage can be sustained or can be bared by any LED, right? So that means what, if I'm providing any voltage to any LED which is greater than 5 volts, so there is high amount of chance that the LED may burn out completely. Okay, so remember one thing, you should never ever give voltage greater than 5 volts to any of the LEDs, right? And based on this particular table, what we had taken out is this. That means what, the VCC is 3.5 volts. That means the maximum voltage which we can give is 3.5 volts, and the current which we know, that minimum threshold current that is required to glow all of the LEDs, that is 20 milliamperes. And since we are dealing with these three LEDs, that is red, yellow and green, so we what we did, we just multiplied this current into 3. That means what, 2 into 3, that means 6, that means 60 ampere, because the current is 20 milliampere. So the maximum amount of current that should flow to the collector side, that is 60 milliampere. Okay, and now I hope that now you might have got to know that why we had not connected this particular LEDs in the series form. Why? Because if you are connecting in series, so this green LED will glow first, then yellow, and see, as soon as the yellow will glow, the green will stop, and as soon as this red will glow, this both will stop. Okay, this both will stop working. Why? Because the IC is moving in green, then in yellow, and then at the end in red. Okay, and as soon as it will move in the yellow LED, this would be in the off condition. As soon as it will move in the red LED, this two would be in the off condition. So that's why we did not prefer this particular circuit, rather we preferred this one. Why? Because all of the LEDs will glow at the same time. Okay, so that's why we had preferred this particular circuit. And now I hope that you understood that why we had considered this one, not this one. Okay, so moving further, we know that IC should be 60 milliampere. Okay, and according to the BC547, the current gain is 110, and thus we had just by using this particular formula, we had calculated this value, that is 0.54 milliampere, right? And then what we had done, we had applied KVL to this base emitter loop, and then by applying KVL, we had got the value of RB, or basically the base resistor, as 5.137 kilo ohms. Okay, and then what we had done, we actually simulated this particular circuit. We provided one audio signal, but what we saw was that the LED was not glowing properly, right? So then what we had done, we had selected the value, this particular value of the capacitor having the capacitance of 4.54 microfarad, and this particular thing, that how we calculated this value, I will tell you in the amplifier section, while designing the amplifier using BJT. At that time I will tell you that how to calculate this particular value of the capacitor, right? So you need not to worry about that. So just by connecting capacitor, we assured that, what we assured, we assured that the DC signal, that means the DC signal would be blocked. That means the DC signal which is coming from this particular terminal, it would be getting blocked with the help of this particular capacitor, right? And at the same time the AC signal would pass. So the AC signal would pass to this particular terminal, that means to the base terminal, right? So in absence of capacitor, the audio signal was not able to superimpose with the DC signal, right? Therefore, to superimpose weak audio signal, since the audio signal was in millivolts, sorry, so to superimpose that audio signal on the strong DC signal, we had connected the capacitor. Okay, so that was the main reason that why we had connected the capacitor. Okay, so for superimposing purpose. All right, and then I had explained you this particular part. Okay, so I hope that you understood each and everything in depth. Okay, and now I am going to put the video which I had implemented. Okay,